There we go. Okay, very good. So let's get started. Looks like we have people starting to join. So good afternoon, everyone. This is the panel on homomorphic encryption. I'm Tomas Vagoun with the National Coordination Office at or for the Networking and IT R&D program in the federal government. And today we have, I think, very exciting panel to talk about a technology that at first seems like magic, but I think we're getting to a point where a lot of things with homomorphic encryption are becoming practical. And we'll talk about how practical and what can we do today with homomorphic encryption, and what the research should focus on to advance this field forward. So I'll begin with a quick introduction of the panelists. I'll start with Dr. Heidi Sofia. She's program director at the Division of Genomic Medicine at the National Human Genome Research Institute at NIH, the National Institutes of Health, where she manages programs and activities in genomics, data science, informatics, focusing on advancing technologies that can help solve problems in genomic biology and healthcare, including how to securely share data to conduct medical and genomic research. Dr. Sofia received BA in biochemistry and master's in public health from UC Berkeley and PhD from the University of Wisconsin-Madison. Next, we have Dr. Josh Barron, program manager at Darpa at the Information Innovation Office, where he manages several programs in cryptography and related applications of cryptography to national and DoD problems. Dr. Barron holds undergraduate, master's, and PhD in mathematics from University of California, Berkeley, and UCLA. And lastly, we have with us Dr. Kurt Rohloff. He's an associate professor of computer science at New Jersey Institute of Technology. He's co-founder and CTO of Duality Technologies. That we'll hear about their work. He's co-founder of the open source Palisade homomorphic encryption software library, an instrumental library in this field. Co-founder and steering committee member of the homomorphic encryption.org industry standards consortium, PI on a number of research projects funded by federal agencies, and he holds undergraduate, master's, and PhD in electrical engineering from Georgia Tech and University of Michigan. So thank you, panelists. Thank you for being here and participating in this panel. Just before we start, you know, a quick word about what is this NITRD, right, in the title. So federal government spends roughly, or invests, $4.5 billion a year in basic research in various networking and IT domains, cybersecurity being one of them. And so that it's spread across, you know, a lot of agencies in the federal government, you know, from NSF to Darpa and others. And it deals with lots of different networking and IT type questions and challenges. And obviously it involves hundreds of people, thousands of projects, and it will be great to coordinate some of that, right? To coordinate the research that is taking place throughout this 4.5 billion roughly a year investment. And that's what the Networking and R&D, the NITRD program or forum does. It's a construct within the federal government to help coordinate this research through coordinating groups, development of strategic plans, you know, establishing priorities, and just having a place where internally program managers and directors and others who are responsible for research can come together and discuss opportunities for, you know, joint research, understand each other's problems and so on. So that's where I am part of helping agencies get smarter about who's doing what and why. And so part of the conference is, right, application of the cybersecurity research. And so what we try to do is bring in the perspective of the federal government and the R&D community and the enterprise behind it. One, to showcase some of the successes and some of the work that the federal government is doing in funding cybersecurity research, as well as provide some view into what are some of the challenges and objectives that the federal government and agencies would put on the table as priorities for research from their perspective. So that helps the researchers and research communities understand, better what the federal government's priorities are. So today we have for the topic, panel and discussion about homomorphic encryption. And as we know, it's a subject with great promise because it potentially deals with solving one of the kind of major security challenges in our field, which is we must first decrypt protected data in order to use it, right? It's all good to have it encrypted when it's addressed, when it's stored or being transmitted, but once you need to do something with the data, you got to decrypt it. And hence it's open now to lots of attacks and potential misuse. So if we could do computation directly with encrypted data, and the result was also encrypted, that only the rightful owners can decrypt, that would solve lots of problems and open up a lot of opportunities, and a lot of potential solutions. So that's what we'll talk about. This is a field that has been patiently funded over the years by the federal government through basic research in cryptography and through some investigations to apply those findings and those technologies to some problems. And I think we're finally at a point where it's worth discussing and taking a stab at understanding what is it that we can do with it today, how is it applicable, how is it practical, and what can we do or what needs to be done to make it more usable and generalizable. So that's what we'll talk about. And just want to again encourage everyone that's in the audience to post your questions in the chat as we go along. And we will address them as they come. All right, so that's kind of my introduction of this topic. What we'll do now is each of the panelists will take a few minutes to summarize, where do they fit in this question, in this field, in terms of their roles, in their agencies or interests in advancing solutions in secure data sharing and analysis in general, and homomorphic encryption in particular. And then we'll move to some more open discussions. So let's start with that. Josh, how about we start with you?
Sure. Yeah, hi. I'm Josh Barron. I'm a program manager at Darpa. So in terms of where we fit, I think there are kind of a number of different layers to that answer on our part. First is kind of, what is Darpa, and then kind of what has our role, what is Darpa's role writ large? What has Darpa's role been within the kind of advanced cryptography area? And then kind of, what lies ahead. So DARPA's been around since the 50s, and its purpose is to prevent or impose technological surprise. The way to kind of think about it is we invest in high risk, high reward research that is kind of intended to be very risky. And if it pays off, you get a lot out of it. It doesn't always work. Often a lot of kind of unexpected things come out of, side things come out of the work that we do. So kind of, I guess, of note, our interest tends to be getting technology to a place where the DoD or in kind of industry would be able to take a look at it and say, oh yeah, this will work, right? So you can think of us almost as a de-risking organization, right? We're paying down risk for the Department of Defense and for private industry. That also means, by the way, that we typically do not invest directly in specific technologies or applications that you often see in the commercial world, because that's kind of more investment of the government's time. DoD can just rely on those companies. They don't need us being like the carrot of telling people to go do this work. So I'm a program manager. What that means is that I run existing research efforts, and then I identify and kind of sell to my leadership what future efforts should be, and then go off and run those. The typical DARPA program in my area is somewhere on the order of, I would say, $40 to $60 million over 4 years. Okay, so why is DARPA interested in cryptography? Well, the idea of, certainly in kind of homomorphic encryption, like the idea of being able to keep data always encrypted while still kind of getting the things you need out of it is kind of a canonical DoD need. And so we started investing in specifically homomorphic encryption. I think going back, I'm going to screw this up, but it's something a bit over 10 years ago, and with a program called Proceed, and that largely focused on fully homomorphic encryption. I guess because I'm the first one to talk, I should say, so the topic of this discussion is homomorphic encryption. It's important to note that there are a number of other, what I would call cryptographic primitives that also do these kind of impossible things using cryptography. So homomorphic encryption is really this idea of really coming out of very much thinking about like cloud computing and thinking about having some very powerful server sitting on the back. And the idea is that could the client offload their work and have this more powerful server kind of do this work for them? But I don't want the server to actually learn what the underlying data is. So I encrypt the data, I send it off to the server. The server does all the compute for me, but they don't learn anything because it's always encrypted, and then they send me something back. And that really was the kind of underlying intention behind homomorphic encryption. There are other kind of paradigms that are possible, like probably one of the more popular ones is distributed computing. And I think that idea at the time, for a whole host of reasons, not least including bandwidth and other things, was a little less popular, but now is kind of network connections are much faster. And just generally, even when we think of a cloud, you think of it as a distributed computing thing. There are other kind of more distributed computing paradigms that also, so homomorphic encryption is really specifically about sending an encrypted blob to a computer. That computer computes on that encrypted blob. There's a broader context called secure multi-party computation that has multiple parties jointly computing on either the same encrypted blob or very often, different kind of components of some kind of encryption, some kind of even distributed encryption. Another technique that you often hear is something called, and then there are like things that you would build off of these primitives. So a classic example is private information retrieval. I want to send an encrypted query and receive a response where the data owner doesn't actually understand what my query was or what the actual nature of the response is. Another primitive getting up into this, and kind of like muddling levels of abstraction, something called a zero knowledge proof. I'm kind of going on at length, but my only point is that there's a very broad world in this space. DARPA has had, I'm going to count now, depending on how you want to count, 8 programs, 7 major programs and 1 small one having to do with these advanced cryptographic primitives. They span from computing directly on encrypted data. So that would be Proceed, a recent program called Brandeis that I ran and just completed. That program looked at very doable examples of these technologies, and I'm happy to talk more about that. We ran more theory-oriented programs called Safeware, and another kind of theory-oriented program I run right now is on Civ, which is specifically about zero knowledge and what possible DoD applications there could be in zero knowledge. And again, I'm happy to talk more about that. In terms of distributed computing, I run a program called RACE, or Resilient Anonymous Communication for Everyone, that specifically looks at how secure multi-party computation could be used to build a very resilient message passing, like a secure messaging system. And then I run a smaller program called Cooperative Secure Learning, about specifically using many of these technologies for the purpose of privacy-preserving machine learning. I guess in full disclosure, we're funding Current as part of that effort. And then finally, we are running a program, not me, but in a different office called Deprive, and that's building a hardware accelerator for fully homomorphic encryption. And because I've already talked forever, I'm not going to say what FHE is because I'm 99% sure that Kurt is going to explain what that is. Anyhow, so the bottom line is there are a number of, okay, where are we going with all these technologies? So I said what DARPA is, and I said the programs that we're running. So to tie that together, all of these programs are different variants of DARPA trying to prove out these technologies. In the case of the very first one I mentioned, Proceed, it was literally about reducing the theory, like the theoretical complexity by 7 orders of magnitude, right? So at the end of that program, you didn't get anything that was like necessarily directly useful, but we proved that we were taking things out from the far theory into the like, hey, this might actually work. And then companies like Hertz have taken that, like literally that work, and dragged it further along to actually make concrete software products. In some of our other programs, so for example, RACE that I just mentioned on the secure messaging one, and Civ to a degree, and this machine learning one, often what we're developing are prototype software implementations. And so not just looking at the theory and trying to de-risk the theory, but taking kind of more mature theory and actually now taking it for like prototype software implementations. The way I kind of think of it is like, it's like the dog that comes into the house with the bird and kind of shows the owner. Like that's what we're doing. Like we're taking these applications, trying to build cool ones, bring it back to the DoD or the broader world and say, hey, cool, you can do this now. Like, don't you like this technology? So that's that really has been DARPA's historical role. Okay, I'm gonna stop talking because that was a long time, but I'm happy to talk more about any of this.
Great. Heidi, let's move over to you. How do you fit in this?
Sure. So I'm Heidi Sofia. I'm at the National Institutes of Health, which is really the largest biomedical research organization in the world. And of course, has been spotlighted recently in terms of developing treatments, diagnostics, vaccines in the pandemic, with results just beginning to come through the door. So my interest in this field is very much in terms of the application to use. So the actual deployment for our missions, our biomedical research missions. And so the larger mission of the NIH, which is to advance biomedical research and health and translation to health. And then in particular, the mission of the institute that I'm a part of within NIH, which is the National Human Genome Research Institute, or the institute that conducts research into genomics. So the use cases can be thought of in that way because, really we think of it in terms of data, types of data, how our scientists are able to generate and analyze and use this data, but primarily that data has a fundamental tie to the people who donate this data. So we have this tremendous interest and need to preserve trust with the human participants who very generously contribute their information so that these really challenging problems can be addressed. So in particular with genomics, so maybe clinical data, interest in privacy preservation of clinical data is shared across NIH. Clinical data is obviously very personal and it's regulated by, legal constraints and definite, very specific structures and hoops that have to be, mandates that have to be followed as far as consent and how that's managed and permissions and so genomics data is all of that plus more, because genomics data is this biometric fingerprint. It's indelible. It's a biometric, like a fingerprint is a biometric, or an iris scan is a biometric. But you could actually burn your fingerprints off. That's not necessarily indelible, but DNA is inescapable. And also it's possible now, the technologies surrounding it are so advanced and so cheap and so sophisticated that just the tiniest amounts can be detected in environmental samples. And it also has to be thought of as a window both into the future and the past, in terms of the future, because we are able to increasingly read health status and make predictions about very subtle predictions about health and progress of potential diseases, risk factors for diseases, but a window into the past in terms of being incredibly sensitive as far as revealing history, not way past national origin, way back into the introgression of Neanderthal genes, or an even more obscure people called the Denisovians, which are, even more obscure than the Neanderthals, in which the only physical evidence of as recently is the tiniest little finger bone. So the power of the technology is tremendous, and it's really beginning to come to the table. And so we have this very strong interest in using the data. Our use cases involve huge amounts of this data. So we need the genome sequences from hundreds of thousands to millions of people to really get at these extremely multidimensional problems that we want to solve. And yet we have this extraordinary mandate to protect it, to use it properly, to adhere to the public trust, because our whole enterprise is fueled off the public trust. The trust is the currency of the realm for NIH, and we're very proactive in protecting that. So that's kind of the gist of my position in this, in that we want to use it, we want to take advantage of it, and we do actually see preliminary applications in practical ways. And I'll just throw one out there. There's the Medco software that was developed at the EPFL lab in Switzerland by Jean-Pierre Houbeau and colleagues. And Medco incorporates homomorphic encryption as well as a few other privacy technology strategies, but is really deployed towards sharing clinical data between different hospitals. So with that, I guess I'll just add that my role is as a program officer. So in addition to looking for technologies on the horizon, we also try to promote the funding opportunities for those technologies, both in terms of research grants, what we call research project grants, and as well as our small business program through SBIRs and STTRs.
Great, thank you, Heidi. All right, let's give a few minutes to Kurt. Not only is he involved in the research aspects, but he's also making money with this. So we want to hear about how is that working, right? So Kurt, tell us about your work.
Well, this is, rather pragmatic way of putting it, I guess, at some level. So, thank you, Tomas, for the introduction, and thank you for facilitating. And like I said, I should also be very grateful, and I am very grateful for Josh and Heidi, who have been supporters of my research and supporters of the research that we're transitioning into practice at Duality. So I have, like I said, I'll give my own take on this, because I've been touching and using, developing, applying this technology called homomorphic encryption and privacy technology for over a decade now. And, in many real ways, I've drank the Kool-Aid on it, to the point where I've quit multiple jobs to focus on it. And been basically dedicated, the past decade of my professional life to try to make it real and commercially viable in many ways. So at Josh's prompting, that the notion of homomorphic encryption, and especially fully homomorphic encryption, is where one can take sensitive data. Great example is genomic data, genetic data, as Heidi alluded to, be able to encrypt it, aggregate it at a data center, and then run analytics on that data while it's encrypted to identify things such as, are there specific mutations that are indicative of certain kinds of rare diseases, like certain cancers, or indicative of specific kinds of afflictions of specific at-risk minorities, for example, that don't necessarily want to share a lot of privacy-sensitive information about themselves. And this very kind of simple concept has really been driven in application by privacy technologies like Josh had alluded to. And the one we focus on, like I said, is homomorphic encryption. And my take is, like I said, along the way is I was PI, principal investigator, leading one of the primary implementation efforts of this Darpa Proceed program, starting from back in the dark, misty times of 2009 and 2010. It seems like ages ago now, but seems also like yesterday. And as Josh, alluded to, it was really a very fundamental basic research challenge where back in those very, very early days, the first implementation that I'm aware of basically implemented one of the original constructs, and it ran in a way where it took a half hour to encrypt 2 bits, do just a bitwise AND operation, and then decrypt the result. And so you think about this half hour to do a bitwise AND versus what people had thought about at the time about moving data centers to the data to the cloud and the cloud applications and things like that. And kind of the mission that the community has collectively been on is about how to take this really kind of gee whiz technology and make it usable, applicable, and really adding value to specific use cases. And I somewhat tongue-in-cheek say that my goal in life is to make homomorphic encryption boring at some level, to the point where you can't actually tell that homomorphic crypto is running underneath it, and nothing really changes. Because whether you have it on or have it off, other than that, you're more effective because you have access and compute on more data. And so, like from these very early days of DARPA Proceed, where effectively the team that I was involved with was effectively a mathematician to FPGA compiler at some level or another, taking equations scrolled on a whiteboard for the first time ever, and going from the path of getting them into MATLAB, getting them into C, getting them to HDL, and then deploying them on a coprocessor. We were at a point where we started to be able to do things like basic signal processing on iPhones and things like that on encrypted data, and basically get things improved by about 6 orders of magnitude. And one thing that we learned early on in those days is that, yeah, the performance was initially a huge thing, and we've knocked off many orders of magnitude since then, probably 10 at last counting. The other challenge that was off, a lot of people didn't realize, that came into a lot of research that we were doing, particularly some work that Heidi was sponsoring with us, and also some work that Josh is sponsoring with us right now, is how to make this technology more general and usable. And the concept and the anecdote I like to use is that when we're born, we have base 10 hardware, and so we learn how to do base 10 math of for computing, searching, sorting, stuff like that. And then we go off to engineering school or computer school, and we have this hardware, like this phone I have, that has base 2 hardware. And so the underlying compute primitive that we have is things like binary search trees and binary algorithms. And if you can stuff something into a binary tree, you're cooking with gas, as we say. But if you want to do something else, it's not so good for things like natural language processing and stuff like that. And then you look at homomorphic crypto, and the underlying compute primitives are things like these, very specialized things called the val add, val mult, that effectively look like vectorized addition and vectorized multiplication, so that if you could, get something that looks like that, compute that looks like that, like signal processing, you're doing really good. But there's a pile of work and pile of research that's been ongoing for the past 10 years about how to take general programming and put it into the space so that it runs efficiently on homomorphic crypto, just with those underlying compute primitives and understanding the performance trade-offs, in addition to better math, better crypto, hardware acceleration of these things, and then to put it all together into something that's actually practically usable. And we're starting to see practical applications of this, like the genome-wide association studies, like VoIP processing, and various kinds of financial applications that Duality's been enabling for being able to query data and encrypt queries and run queries on data and things like that. And we see a lot of the early use cases of our paying customers, and both across the board, as being not so much about a pure cloud play, which was the original vision, but the notion of how to basically make data more accessible. And the example I like to give is, for example, like the use case that Heidi had alluded to, which is that, and right now, for organizations to share sensitive data, typically the lawyers have to get involved. Get data use agreements, get NDAs, sign away your firstborn, any of these number of things that you have to do to kind of get access to data. And what we found is that a real major benefit of these privacy technologies isn't necessarily like a pure cloud play, but is to reduce legal friction, to make the data use agreements and make the legal agreements much more easy and more rapid, so that when one wants to run a, for example, a genome-wide association study on aggregated data, it takes on the order of minutes to run these queries, as opposed to, or seconds or milliseconds, as opposed to weeks or months of legal time to kind of get these in place. And in some sense, this is, one of the major applications of privacy technologies is to help enable trust. And the other side of that, and kind of bookend to this, is that trust is not just about hey, these things exist and we can wave a magic wand. It's built around openness in terms of open academic research, in terms of the protocols that are being used, which of course is Josh was very involved with the early Proceed days and things like that, and Race and Civ and whatnot. It comes with open source implementations of these crypto implementations, so people can look at it and know it and trust it, which is what we're pushing on our Palisade homomorphic encryption library community, and the uptake we've been getting from our user community and a number of both major operating systems and defense contractors and government contractors, and then our broader efforts for standardizing crypto, which is to standardize parameter settings, which we've done in partnership with organizations like Intel and IBM and Samsung and a number of the other major players. And this notion of a trust chain going from designs to implementation to usage is a major part of engendering trust and going forward from there. And how we're starting to get uptake, not just from homomorphic crypto as a research project in and of itself, but homomorphic crypto as an enabler for applications, an enabler for research. And so, for example, using homomorphic encryption protected genome-wide association studies to enable clinical research, and going forward from there and pushing it forward not as a research project, but as a research enabler, which we see as the major benefit for, like I said, in the genomic space, and also, like I said, for protecting against financial fraud and other kinds of things that we're doing commercially also on the other side of Duality. So thank you.
All right, thanks, Kurt. Just a reminder to the audience, if you have any questions that are coming up to your mind, fire away, put them in the chat. So we have this exciting field, right? We have this idea that we can directly compute with encrypted data. Let's take a quick sidestep. Josh, can you give us a brief sort of understanding of what is this homomorphic encryption? Why does it work? Why is it secure? And what sort of problems can be addressed by homomorphic encryption? All right, in less than 4 minutes.
Oh God. So what is this homomorphic encryption? I mean, so it really comes down to, okay, so I won't give you the total, okay. So homomorphic encryption is the idea that if I take encryption of X and encryption of Y, and then I multiply encryption of X and encryption of Y together, I get encryption of, for example, X plus Y, right? So encryption of X times encryption of Y equals encryption of X plus Y. And the idea that I can perform mathematical operations on the encrypted data, and it preserves the underlying kind of secrets that the encryption was already trying to do. So that's what that is. Fully homomorphic encryption, by the way, is when you can perform what are essentially like arbitrary mathematical operations on the underlying unencrypted data, like on the kind of messages, whereas partially homomorphic encryption is when you can only do one operation. And I guess I would say, this is not entirely accurate, but it's a good stand-in. Public key encryption, largely speaking, is homomorphic. That's a vast overgeneralization, but it's a good, if you want to think about like what the underlying efficiencies of these things are, like doing fully homomorphic, like the cost of, say, doing one of these arithmetic operations is roughly a public key operation. It's roughly the cost of, your more expensive of encryption or decryption. Fully homomorphic encryption historically was a couple of orders of magnitude more expensive than that. These days, it's kind of more complicated. Again, I defer to like the actual complexities to Kurt. So wait, that's what the technology is. Why you would want it? Like a really standard application is database access. So I want to store large data and perform and do queries against that data. So a lot of the early applications that you saw and you still see are especially things like exact match queries. So things like there's a large unencrypted data set and I want to see If there exists a string of mine in that data set, but I don't want to reveal the string, sometimes it may be that the encrypted, it could be you know, what is or is encrypted versus unencrypted can kind of vary, but that's a very, very common example. One of the things, for example, that we looked at with the Undersecretary of Defense for Personnel and the R in that, I always forget, records, is suppose like the Air Force wanted to talk to the part of the federal agency that is in control of like food stamps, and they wanted to understand how many of their service people were on food stamps, but they wanted to look at it by a social security number. So like the Air Force would send all their social security numbers to the folks who you know have the food stamp records, and then they would like send back a response. But they didn't want to actually reveal the social security number. So could I send you the social security number encrypted and you send me back a response, but as a result, you can't even know what exactly the response was? Because if you knew what exactly the response was, you could kind of back out like that, who I was querying for. And it turns out you can do that. And it turns out you can do that at US population scale. So hundreds of millions of records with millions of queries. It takes on the order of minutes. It's not hard. And so anyhow, so those are reasons you would want to do it. I guess the one thing I would just say is that it's really annoying, but I can almost always, given a very concrete specification of what you want to do, tell you whether the application is doable or not. However, it is the case that minor changes, like standard minor changes in like how people would normally think about doing computations, create massive inefficiencies when it comes to cryptography. A lot of those have to do with the fact that much of the way we think about programming is you're running algorithms that are already contextual with the existing data. So you're running like a for loop, or especially like a while loop. You can't really do that as an encrypted thing, because the whole point is that you actually can't see the data you're encrypting on. And so a lot of those kinds of contextual algorithms, like while x is less than some value, you're not going to be able to do. Likewise, when you're doing this encrypted search, again, the way you come, like the very classic example is binary search, right? You look in one half or another half, and then you throw the other half away, and then you start going less. You can't do that with encryption when you're computing on encrypted data. And the point is because, again, you have to compute over the whole set. So they're like, that's just kind of like just giving a glimpse as to why these things start getting kind of weird when you look at actually doing them. Maybe that was 4 minutes. I don't know if I answered everything you asked for.
Well, yeah, I think, you know, you gave us some perspective on, you know, how does it work? And, you know, it relates to a question we have, you know, on the chat. You know, so, right, we heard this kind of idea, right, back in the 70s, maybe this is possible. And then it wasn't until, right, 2009 and Craig Gentry's PhD that he proposed kind of this generic framework for, you know, doing a lot of the algebraic, right, computations possible. And then we heard about this 10 orders of magnitude improvement from kind of the general idea to, you know, what we can do today. What happened, what was done to go from, you know, something being, you know, 10 orders of magnitude slower than what we're able to do?
So that is I'm going to, honest to God, Kurt's probably, so I'm going to answer it in the kind of philosophical way, and then I honestly really would defer to Kurt, who I think knows much more the kind of nuts and bolts. But the way to think of it is you have to understand how these things are being developed. These are being developed by computer science theorists. And in the computer science theory world, when we say efficient, what we really mean is computable in probabilistic polynomial time, right? So like it could take like the heat death of the known universe, but if it's asymptotically efficient, we're going to declare victory, right? And so when Craig Gentry's initial paper came out, it proved that fully homomorphic encryption was possible. Then getting from to an actually practical solution has taken, frankly, it's actually not taken that long. It's taken about 10 years. By contrast, like zero-knowledge proofs, which were invented in the late 80s, have only seen like really massive use of it only in the last 5 years, kind of 25 years later. So the progression here generally is that the theorists come up with, you can call it like an existence proof. And then what often happens is, frankly, that exact model is often not the one that's then used. Like once you kind of prove that it's possible, a bunch of other folks come in and give other variants of what it, trying to do the same thing a different way. And then you get the applied cryptographers coming in and like making it actually much more efficient. And then you get companies coming in and saying, okay, not only is it like now kind of theoretically efficient, but now I'm integrating it into a broader solution. So there's really a whole kind of pipeline of innovation that has to occur to get something from a PhD thesis saying you could do a thing. Also, not for nothing, even the original Gentry paper had some, actually, have we actually done away with the circular assumptions? I don't even know. Oftentimes, even like when you have the initial theoretical stuff, there are weird security assumptions on the side that you'd often like to take away before you actually get into the real thing. You know, there's a whole sordid tale having to do with a different kind of cryptographic technology called indistinguishability obfuscation, which is very much, you know, so it's a whole, this happens all the time in crypto, where you have things that are theoretically possible, and then the real question is, but could you actually do it? And what's super annoying is that, again, the theoretical answer, can you do it, is almost always yes. But again, it's so freaking inefficient that actually doing it is a disaster. And so when you get into like, I would say like muggles, so people who don't have deep expertise in the cryptographic world, because why would you? You have like better things to do with your life. It's very difficult to bridge that gap between someone who has like a data need and then that PhD person who all they think about is like, oh, it depends because there's this, that, and the other. And that's actually why, again, just, you know, plugging Kurt, the work that, you know, he and other companies in the space do is so valuable. They're really pioneers in normalizing this technology, whereas we're often, again, at DARPA, mainly trying to just prove what is or isn't possible, by and large, not always.
Hi, this is Heidi. There's actually a question in the chat that I'm very curious about, and so I'll just raise it here. How will quantum computing impact homomorphic encryption?
I can take that or Kurt. It's either.
Why don't you take it, Josh, and then I'll actually, there's a bunch of things I want to build off on what you said already. Anyway, yeah.
Sure. Okay.
Yeah.
So right. So all of public key cryptography is based off of, well, all the good public key cryptography is based off of what they'll say is like, this encryption scheme is secure as long as this math problem is really hard to do. So the very first, like, you know, first public key schemes ever were RSA and El-Gamal. Those rely on, respectively, the hardness of factoring numbers into primes and finding a discrete logarithm. Those are still hard problems today. Were a quantum computer to exist, those would not be hard problems. Whether a quantum computer is going to exist in the near term is kind of neither here nor there. That's just the important part to understand about, well, you know, about quantum. And so what we've been looking at is so-called post-quantum algorithms. So what are math problems that would still be hard even if a cryptographically relevant quantum computer were to exist? And the reason I now say like cryptographically relevant quantum computer is that there exist quantum computers now, but they're like really weak and they can't really do anything useful still of any kind, let alone solve a problem like Shor's algorithm. Shor's algorithm is the quantum algorithm that would break a lot of these things. So the good news is, I'd have to look back at the original paper, but I think even the original Gentry result, I think was based off of LWE, which is what's called learning with errors. It's another kind of math problem. And LWE is not assessed to be breakable or any more efficiently breakable by a quantum computer. And so a lot of NIST right now is running a competition. DARPA does not typically have a role in saying what is or isn't quantum hard. NIST does a lot of this work, National Institute for Science and Technology. They have a very kind of open forum for doing these kinds of discussions, which is very important when you're trying to agree on these kind of standards. And so the long and short of it is, there are a number of other math problems that are assessed to be so-called post-quantum. So even a quantum computer wouldn't solve them efficiently. Why didn't we use them in the first place? Two different reasons. One, because maybe we weren't smart enough and we weren't thinking in these terms. But the second part is the post-quantum algorithms tend to be a little slower. Not always, but like they tend to be at least a little slower. You're paying some kind of price. And again, we can go into more detail. While we're on this topic though, I'd be really remiss if I didn't just point out symmetric key algorithms. So like AES or DES or any of those things, or SHA-2 as a hash function, are not meaningfully weaker from a quantum computer. So and there's this tiny tweak to that answer, but basically, so if you're ever having someone tell you that like a quantum computer can like break current hash functions or break current encryption, that is basically speaking not the case. So I just want to say that because that sometimes people think that like quantum breaks all cryptography, and that's just not true. Okay, that's what quantum is all about. So again, the good news is sorry, just to take back, almost all the current fully homomorphic encryption schemes, and certainly most of the things you'd want to do in homomorphic encryption are very possible to do in a post-quantum world.
Right, and that's
Right.
actually what. Sorry.
No, I was going to say, Kurt, what do you would you like to add to that?
No, this is a kind of a great tee off, Josh, for a number of things. For one, I completely you got to we're in complete agreement about the post quantum nature of AES, DES, SHA-2, but also about the value of the homomorphic crypto stream. And what we found is that specifically when we start to deploy homomorphic crypto technologies in production environments, what we found is that because a lot of the CISOs of large enterprise organizations like banks, like healthcare centers and things like that, they pretty much have quantum attacks on their mind and post-quantum crypto on their mind. And often they're very receptive to homomorphic crypto, particularly post-quantum homomorphic crypto, because they want to get a taste and a feel for what this technology looks like before they actually really need it and required to do so. And so it's like one of these things where the CISO's office, often they're a cost center instead of a profit center. So they usually give approval or not approval of things. And it's like the old joke about lawyers, and no lawyer ever got fired for saying no. No CISO ever got fired for saying no also, although it's kind of debatable. Typically they approve, a lot of the post-quantum homomorphic crypto techniques just so they can get used to it and get ready for the future. The other side then is also bring it back about, what made, and this, kind of to build off this, what made homomorphic crypto what it is and what pushed it forward. Fundamentally, a step above the kind of like the nuts and bolts of what we actually done. What made it possible is vision and funding. And I don't want to underplay this enough. Organizations that are set up to take on risk in ways that companies never would actually ever be able to. And I'll say this as someone who was a longtime DARPA PI, someone who was an academic for a few years, and now someone who's basically a co-founder, is that the technology would never get where it was right now without the most important VC in the world, which is the U.S. government. Whether it's through DARPA, NIH, IARPA, or whoever, to basically take off and as Josh said, de-risk this. And actually, Josh, I love what you said about how homomorphic crypto has moved too fast, because the very first PM at DARPA that funded this was a gentleman by the name of Drew Dean, who I have tremendous respect for. And the story he shared with me once, and he might have shared this also with you, Josh, at some time, was that when he sold Proceed and sold the vision of homomorphic crypto, he gave the example of looking at past crypto systems like RSA. RSA, it was discovered roughly in the early 70s. Just practical use sometimes the early 90s with the internet. It took about 20 years. You look at elliptic curve. Discovered in the 80s, started being used with Blu-ray players. 20 years. You look at homomorphic crypto. Well, discovered in 2009. Give or take a year, depending on who you ask. And practical use, well, hey, there are multiple startups. We're not the only player in this space, and there are multiple big companies that are involved with this also. It's a 10-year time frame. And Drew said that he wanted to get DARPA in the game, specifically so the U.S. government could use, and U.S. society and world society could use homomorphic crypto not in 20 years but in 10 years. And look at us, this person with this notion of vision and risk, made this investment at the exact right time and pushed it forward. And that in some sense is, I see as the major enabler for where we are right now. The other side of it though is what actually happened. It was a huge community effort in terms of nuts and bolts of what happened. There was top-notch theorists, Shafi Goldwasser, Turing Award winner, Vagoun Vakudanathan, kind of a who's who was involved with these various kinds of projects and communities over the years. There was a lot of fundamental work in algorithm design that went into this. A lot of systems and hardware work about how to make these things actually just run fast, to understand, were the design patterns from embedded signal processing that we could start to apply to these, very kind of hairy lattice-oriented math. And then what really actually drove us and really kind of pushed it forward was beyond kind of the initial genesis of Proceed was, application need, like the genomic applications that Heidi's been advocating for, like some of the financial applications we've been looking at commercially, like some of the other various applications that Josh brought up, coming from different parts of the US government also. And, whereas, interest and vision and stuff like that got us started, but was the real need of these technologies have driven us into applications where we start to add value and start to solve real world problems. And so it's a kind of a really nice kind of vision push and pull that got us kind of, this in some sense, this traveling circus to where it is right now. And it's been a wild ride, and it hasn't stopped, and I want to keep it going.
Go ahead, Josh, do you want something? I was going to continue the thought. So we've, seen tremendous improvement, right, in the theoretical side of things, from, kind of the general provability or the fact that it is, possible to these 10 orders of magnitudes improvements, a lot of different math that went underneath to make it possible, some commercial applications of it. But as we heard already, right, it doesn't solve everything, right? And some problems are more suitable, some are less suitable for application of homomorphic encryption. So let's talk about a little bit about, what are some of the limitations, whether they are theoretical or engineering or deployment of these techniques. And let's start with you, Heidi, in the medical research and in the ways that you and NIH is trying to use these techniques. What sort of limitations do you encounter with these techniques?
Well, I would say that it's a matchmaking problem, that our data tends to be large and extremely messy and not always, well formed. It's data, we rely more on data intensive computing than high performance computing. So there's a lot of work to do to map the kinds of things we need to do with our data with different kinds of technologies. And so in the near term, it'll be, kind of specific places where those connections can be made. And then there's actually, really significant investment at NIH overall to kind of improve the way that biomedical researchers produce and handle their data. So it's kind of like the transition between, a cottage industry, independent academics, researchers producing data for their own use, and then not really making it available or sharing it or annotating it or documenting provenance or, formalizing the metadata in proper ways so that it can truly be, shared with others in more robust ways. So there's a lot of interest in that problem. And so what that means is that there'll be larger and larger and larger amounts of data that really are formed and suitable for different kinds of more advanced computing technologies. And of course, today we're talking about homomorphic encryption. So that's the space that we're in. So maybe the types of applications in the beginning will be, more defined, but they will help build a foundation for more and more ambitious use.
Okay, thank you. What about you, Kurt? What sort of limitations are you seeing in deploying these technologies?
That's a great question. I get it all the time. So, there's a number of things that we tend to wrestle with as we're deploying these kinds of technologies. And as Josh said, there is often a gap between theory and practice in terms of, crypto and application of crypto. And as Josh mentioned, one of the natures of homomorphic crypto is that theoretically you can do anything. the question, especially for me as CTO and co-founder of a commercial startup, is that we have to find applications where people get value and not just theoretical value, real value as opposed to theoretic value. And the way I tend to describe it is that there's a set of things that we figured out how to do really, really well already. A lot of these basic genome-wide association studies, all these kind of private query capabilities for financial investigations that Josh mentioned. These kind of signal processing things for voice over IP processing, those kinds of very well-defined applications with specific need. And the analogy I give is kind of like in the early days of computing, where it was like the DoD was looking at things like artillery tables and things like that for early compute devices. And I think that's an apt analogy. And what we've also found is that there's a set of things that we'll probably never actually be able to do with homomorphic crypto really well, and maybe even for other privacy technologies. The early example I like to give is things like natural language processing. We'll probably never have the throughput and low latency enough to do really good, general style natural language processing of processing completely unstructured data and things like that, except for specific applications like keyword search or image processing using like convolutional neural nets and things like that. And in between, there's a very large gray space of things that we think we know want to do, but not quite, or haven't quite gotten to yet. And and this is the nature of the work that we've been pushing. A lot of it funded, or a big chunk of it funded by Heidi and Josh, is figuring out what are these kind of applications are in the gray space, and how we try to pull it back into this realm of the possible, and this realm of the practical right now. And that is really the major aspect of research that we engage in right now, as part of the commercialization activities that we engage with, is sorting out what are these gray space things that have value that no one else has really figured out yet that we can start to focus on. But there are a number of things that we haven't quite touched yet. We probably won't touch in the immediate future. Things like unstructured data processing and things like that. But then again, like I said, this analogy I like to give about early computing in the early days, about initially programming with for artillery tables and things like that. You even think back in the 80s and 90s, folks really didn't think natural language processing was all that feasible or practical. And wait 20, 30 years, it becomes feasible. Maybe we'll have that moment eventually where things will start to increasingly become practical with homomorphic crypto. But like I said, these highly structured data processing are things that we generally don't like to touch. We like to focus on things that are highly structured numeric data is a real sweet spot for us, which is why we like to focus on genomic applications, why we like to focus on financial applications and signal processing and things like that.
So I'll just say that Kurt's mentioned a few times now analysis technique called GWAS, genome-wide associations. And I just want to kind of make this real for you. So GWAS is the technique that has allowed researchers with incredible speed to look at the people who are infected with COVID who have severe reactions and determine 4 or 5 main parts of the genome that are responsible for that. And one of them being, some of them being very plausible. So subtle differences between people in their interleukin-1 genes and gene responses. So it's a real key example. It's not everything that we want to do by any means, but it's a really important example. And I'll just point out that Kurt and Duality have published a paper in Proceedings of National Academy of Sciences about this use case. So it might be interesting to look that up.
Heidi, thanks for the plug.
This relates to, this relates to some of the questions we have on the chat, right? In terms of what are some of the limitations and what are some of the good uses or efficient uses. So a question from Saurabh: if the market demand for such protection in database access is so high, why haven't other less secure but more practical schemes like searchable symmetric encryption have taken off in a big way?
So I can. So searchable symmetric is a really interesting case, and the way to kind of think of it is the following. one of the reasons, one of like the really easy examples of like a thing that you would want to do with data, but is really inefficient to do is a join. Basically, I have database 1 and database 2. I want to combine them based off of some kind of common data that they have in the middle, but it's both sides are encrypted. And the reason why it's so expensive is because everything is so encrypted. If you have, table of length m, m and table of length k, you're going to have to do k times m public key operations, more or less, and then plus a bunch more of other kind of gross things. Techniques like searchable encryption and things, or so-called like deterministic encryption, order preserving encryption is another example of this, are encryption schemes that answer the question, well, what if there's enough structure in the encryption output so that I can tell just enough about the encrypted output to do some more efficient computation on it, right? So one way to think about that is like a really easy way to do matching, for example, is you take inputs and then you just hash them, and then the hash kind of hides the input, but then you could compare the hashes, and if the hashes are the same, then you know that the original inputs are the same. The problem with that is that that's also inherently leaky. If I take a data and I hash the whole thing, I'll be able to tell the frequency of, I may not be able to understand what the actual inputs are, but I'll be able to tell, for example, the frequency of the inputs, because all the things that are the same are going to hash to the same thing, and you'll be able to see. So that's an example of leakage. So the challenge gets to be that there are certainly some academics who'd fight me for saying this out loud, but we don't have, it's hard, all of the general work that we do in crypto is based on these so-called mathematical proofs. And these mathematical proofs are exceptionally conservative in what we assume the adversary is capable of doing. When we start talking about these notions of, well, I only have to leak a bit amount of data, and it starts sounding kind of intuitive, I think one thing that cryptographers have learned through like decades of practice is that you give me an inch and I can almost certainly take a mile. Or put a different way, you could use this data, but in one application space, but then you reuse it in a different application space and you're having a terrible day. So as an example, specifically with like searchable symmetric encryption or order preserving encryption, even order preserving encryption, if the data I'm encrypting was already more or less random, so like unique identifiers where you're not talking about time series data, I'm not too worried about what I'm revealing. If it's person level data or things where like, again, the kind of, you have a lot of like common inputs in the same data, you start leaking a lot more about the structure. And so it just gets to be a much more, it gets to be a very nuanced conversation, and a conversation where we have kind of less good answers, but they're very attractive because they're dramatically more efficient. And so I don't want to like crap on it entirely. I'm not saying that there's no place for it. Like Senny Kamara over at Brown has done exceptional work in searchable symmetric encryption, and a whole host of others. I think Microsoft Research, if I'm not mistaken, has done a bunch. So I don't want to just kind of outright throw it out, but there are things that give you pause about it. So yeah, hopefully that's given some window as to why you would want to be worried about something.
Okay. So related to that is the role, not really role, but the data itself, right? In terms of practicality or what's possible or the limitations, right? So there's focus also on what the data is or should be in terms of driving what can we do with homomorphic encryption. Can anyone discuss the role of the data pre-processing, or what sort of data is useful, or in what sort of way it should be presented for analysis to make this work?
Well, I'll say from our experience, sorry, Josh, if I'm cutting you off. Yeah, so what we have found is that generally, as Josh said before, one of the challenges with homomorphic crypto in practice is that it basically, masks the data. Not mask is the kind of a tool or whatever term, because that means something else. But it basically hides the data, and so it's kind of like you're it's like trying to like work on an engine or something like that, or trying to fix your car when the light's off and you're blindfolded in some ways. That sometimes you can kind of just know what you're doing and things just work. But other ways, if you don't know what you're doing, or if things are in kind of the wrong places, then you're not going to be able to be effective with these kinds of things. And so the way I kind of describe it to kind of early users or interested users is that the more you can structure your data with well-defined schemas, so you can kind of handle what you're doing, the more that you can make sure your data is relatively clean and germane to the application that you have, the easier time you're going to have with things. And structure is overall, like I said, very good, which is, like I said, why we tend to focus on these applications with well-defined schemas, well-defined formats of data, and where we have it gives us a sense of robustness in terms of the kinds of compute that we actually work on. And data preparation is always, data scientists in general, and I say this with, because we do have a big data science team at Duality. Data science in general, a lot of the advances of data science are predicated on data preparation and data cleanliness. And the more that you can prepare the data to conform to a schema, the much easier and more effective you're going to be when you start applying these privacy technologies in general, not just homomorphic encryption.
Yes, so switching a little bit, because we are getting to the end of the panel soon, let's talk about sort of research perspective, right? Let's talk about the challenges that you see in this field. What sort of research do you envision would be useful, and why would that be, a productive way of advancing the field? Let's start with you, Josh.
Yeah, so so there are kind of two ways to take it. One, again, so right now we started a major push in zero knowledge, which is a very it's actually kind of in a certain way the dual of homomorphic encryption, in that homomorphic encryption is about computing on something, whereas zero knowledge is often giving a proof of what you have already computed. But as a result, because it's that kind of after the fact thing, it turns out you can do dramatically more complicated things much more efficiently for a whole host of reasons. So we have a major push in that right now about, can I give a mathematically verifiable public statement of sensitive information without actually revealing the underlying sensitive information? So could I have proved to you that, for example, a machine learning classifier was built only using appropriate data without actually revealing what the underlying data was, as an example? And that's eminently doable. Again, with a giant, it depends that your average cryptographer will have to tell you. I will say in the homomorphic encryption space, or in this kind of computing on encrypted data space, to me, by far the most glaring current hole is its practical use. It really shouldn't be. It really shouldn't be that you need a PhD cryptographer to build every single software piece for you. Like it's just ridiculous. What we should have is, I should be able to take C code and immediately, take C code or take whatever, pick your favorite language and compile it into a cryptographically, homomorphic encryption style algorithm. And in fact, IARPA had a program on this called Hector that ran for about 2 years and then unfortunately was canceled. That work is, I guess, outstanding. By outstanding, I mean needs to be done. And by far, that would be the program. It would basically be like homomorphic encryption for muggles, like truly. Like, how can I take, and there's real work here. There's work in, there's actually a lot of really interesting kind of programming language compiler work to be done. There's a lot of work in also like kind of high level specifications of what the underlying expectations you have for what the system ought to be. So there's a whole effort that really needs to be done there. If I had by far, that is the most foundational thing that needs to be done in my mind in the near term. There's like application chasing stuff. I'm sure we could do more things to help folks like Heidi. But in terms of like that kind of like very foundational, directly applicable broadly stuff, for sure, for me, it's that.
Okay. Heidi, what challenges do you see in this field, and what sort of research would you advocate for?
Well, our challenge is it's a perception. One challenge is a challenge of perception, in that there's a resistance to anybody standing between a researcher and their data. So there's often this kind of unwillingness to even really understand what these different privacy technologies can do, because of the perception of, you just want to make my work harder. It's it will slow me down, it will limit me, it will cause problems. So the challenge is creating platforms that making it transparent, really, for the users, and emphasizing how it benefits them, and but also, another challenge is there's kind of a willful blindness about the risks of many things that we do. That we create a policy, and it by very well-meaning people, and it can be very well implemented, and yet there's a divide between the policy world and kind of the governance world, and what the level of protection or the actual effect that is actually the result. So it's a challenge that there's not more of a systems view on risk, or more kind of integrated view of risk and benefit and protection and enabling of research. So partly it's a challenge of communities being able to come together and understand the problem in different ways. So that's the gist of it. I just want to say that there is some research support for mathematical approaches in the privacy field. You can potentially get that kind of work funded at a more mathematical and fundamental level in the National Institute of General Medical Sciences. That's a place to look for math-based applications but then beyond that, other institutes might support this kind of work, including the National Library of Medicine or NHGRI, the Human Genome Institute. But then you have to kind of tailor it more to the application or mission of the particular institute.
Great, thank you. And Kurt, what is your take on research?
Great. Actually, Heidi, I like this angle that you had about research for legal aspects, policy, and risk. As a technologist who's been basically trying to commercialize this tech, we bump into lawyers all the time, and they want to know what kind of government policies are, what kind of government liabilities there are, what kind of things like that. We have, we engage in these kinds of conversations all the time. And we engage with policy researchers all the time to help us write opinions for what actually is the adoption methods and justification, for example, for the GDPR and CCPA. And I actually, that's, as a technologist, is a whole area of research I actually completely didn't understand until I actually had to depend on it. But so that's actually a really great point. I think we underplay sometimes as a community. For us, I'll actually try to get a plug in also. We have our open source library called Palisade, which was heavily funded by NIH and Darpa and used by a number of people in the community. Palisade Homomorphic Crypto Library, for any of the attendees that want to use it or apply with it or play with it or work with it. I take more of like a systems out, middle in type approach to the kind of research that I think is worthwhile. There's a lot of theory that's been going on in homomorphic crypto. I still think that there's work to be done, although there's only so many places that one can do that kind of work. I still think systems and hardware have been relatively untouched in many ways, in terms of systems of how does one get these things to run very well on a CPU-oriented processor when the underlying primitives are very vector-oriented. And then how to use vectorized processors like FPGAs or GPUs or any kind of other things to make it real in some sense. And the other side, which is very true, what Josh said about applications, we have this view of like using homomorphic crypto from one of the bare bones libraries like Palisade. It's kind of like buying a processor from Intel. You'll get a compute engine, you'll get an assembly language, but then to use it, you got to either program an assembly or build a stack of tools like an operating system and programming language, and then libraries like NumPy and scikit-learn to make it real. And there's a lot of fundamental building blocks that go into the syntax and semantics of like how does one translate a C to FHE circuit type compiler. And I'm totally on board with that vision that Josh was saying, is that when Hector was a thing, it was I think a great vision. I still think that problem, like Josh said, as a technologist, is a box that has not yet to be checked. And so, but it also creates spaces for boutique companies like Duality, where we're basically trying to bridge that gap for commercial application and sell more bespoke kind of turnkey type solutions to bridge that gap also for applications of value.
Great. I think we're pretty much out of time. I want to thank all of you panelists for joining, giving us perspective on this field and the challenges and the way forward. So again, thank you so much. We're definitely out of time, and thank you all the participants and the audience for joining us. I hope this was very useful. And with that, we're adjourned, and I'm going to end the meeting. So
Thank you all.
Thank you.
Thank you.